scheduling. So, CPU scheduling is the basis of multi-programming operating system. By switching the CPU among processes, the operating system can make the computer more productive. So, of course, the basic concept, maximum CPU utilization obtained with multi-programming. So, CPU I/O burst cycle. Process execution consists of a cycle of CPU execution and I/O wait. CPU burst distribution. So first, what is CPU burst? CPU burst is when the process is being executed in the CPU. And I/O burst or input output is when the CPU is waiting for input output for the execution. So basic example of histogram of CPU burst times. So here is a small diagram in which the alternating sequence of CPU and I/O or input-output bursts are depicted. Here we assume that a process has begun its execution and there are some of the operations that are performed during the execution of a process. So here we see there are some operations that is load, store, add, store, read from the file. So these are the operations that has to be performed in the CPU. So the process requires the processor or the CPU for this to happen at this time. So the process is using the CPU at this time. The process is using the CPU burst. So and after that this operation is complete, the process is waiting for some input or output operation to be performed. So here it is waiting for input output at this time. When it is waiting input output, it is not using the CPU, and at that we call it input output burst. So this, and then again after the wait was complete, there are some other operations. So this is the state, store, increment, index, and write to file. And again, within the half of the CPU, we call it CPU burst. And again, similar, it comes down and has to use some of input output operation. So it is waiting for the input output operation to be complete, and there we have our CPU burst again, or IO or input output burst again. And we moving forward, there are some operation like load, store, add, store, read from the file, which is similar to this one. So we already saw that this is kind of operation that requires the CPU. So this is again CPU burst, and then it is again waiting some input output operation to be completed, which is known as the IO or input output burst, and this pattern will continue until the process is terminated. So when the process is going to be terminated, there will be a final CPU burst in which the system will request for the termination of the process. And once that is completed, this process will be terminated, and then the CPU and IO or input output burst cycle for the particular process will be finished. So that is what we mean by the CPU burst and input output burst or IO burst. And here we have seen an example of it happen. So the CPU scheduler, so select from among the process in memory that are ready to execute and allocate the CPU to one of them. So CPU scheduling decision may take a place when a process switch from the running to waiting state and switches from running to ready state, switches from waiting to ready, and then terminate. So there are two main types of CPU scheduling. So this is the preemptive and non-preemptive scheduling. So preemptive scheduling is when a process transition from a running state to ready state or from a waiting state to ready state. So non-preemptive scheduling is employed when a process terminates or transition from running to a waiting state. So that's so dispatcher modules give a control of the CPU to the process selected by the scheduler. So this involves switching context, switching to user mode, jumping to the proper location in the user program to restart that program. So dispatch latency time it takes for the dispatcher to stop one process and start another running. So this is the scheduling criteria. CPU utilization, keep the CPU as busy as possible. Throughput, the number of processes that complete their execution per time unit. Turnaround time, amount of time to execute a particular process. Waiting time, amount of time a process has been waiting in the ready queue. Response time, this is the amount of time it takes from when a request was submitted until the first response is produced, not output for the time sharing environment. So this is the scheduling algorithm optimization criteria. Max CPU utilization, max throughput, minimum turnaround time, mean waiting time, mean response time. So this is the first come, first serve, or FCFS scheduling. So first, what is first come, first serve method? First come, first serve method is an operating system scheduling algorithm that automatically executes queued requests and processes in order of their arrival. It is the easiest and simplest CPU scheduling algorithm. In this type of algorithm, processes which request the CPU first get the CPU allocation first. This is the manage with FIFO kiwi. That full form of FCFS is the first come first serve. So this is the example. First, we have the first example. Considering the following set of process that arrive at the 0. So if the process arrive in the order of P1, P2, and P3, and are served in FCFS or first come first serve order, we get the result shown in the following this Gantt chart. So the waiting time for P1 is equal to 0 millisecond, P2 is equal to 24 millisecond, P3 is equal to 27 milliseconds. So to compute that, to get the average waiting time is 0 plus 24 plus 27 is equal to, and divided by 3. So we get that 17 milliseconds. So this is the second example. So if the process arrive in the order of P2, P3, and P1, however, the result will be shown in the following Gantt chart. So the waiting time for P1 is 6 milliseconds, P2 is 0 milliseconds, P3 is equal to 3 milliseconds. So to get that average waiting time, 6 plus 0 plus 3 is equal to, and divided by 3 is equal to 3 milliseconds. So this is much better than the previous case. So this reduction is substantial. Thus the average waiting time under the FCFS or first come first serve policy is generally not minimal and may vary substantial if the process CPU burst time is vary greatly. So this reduction that we saw in these two examples is a great reduction. That means there is a great difference between the first and second example. The average waiting times were really different, 17 and 3 milliseconds was a great difference between them. So the average waiting time in this is not minimal generally, and if may vary substantially depending upon the burst times of the processes and the order in which they arrive.
Shortest job first scheduling, or the SJF. It is associated with each process, the length of its next CPU burst. Use this length to schedule the process with the shortest time. SJF is optimal. It gives minimum average waiting time for a given set of processes. The difficulty is knowing the length of the next CPU request. So, SJF is ginagamit niyang criteria in choosing is yung burst time. Tinitignan niya kung sino yung may pinakamaliit na burst time. So, pag mas maliit ang burst time, mas mabilis ang computation or the completion process ng task or yung job na binibigay natin with the CPU. Start tayo sa pag-drawing ng Gantt chart. At yung Gantt chart natin is laging nag-uumpisa sa time 0. So, ang sabi ko kanina na ang criteria is yung sa burst time. So, ang may pinakamaliit na burst time dito is yung P1 at P3. Pero wala sa kanila ang mauuna dahil gagamitin lang ang criteria na burst time once na nagkasabay-sabay yung process sa RAM mo. So, ang mangyayari, ilalagay natin dito yung P4 dahil ang una mong titignan dito ay kung nag-arrive na ba yung process. So, si P4 at time 0 ay gumagamit ng burst time na 7. So, mag-i-end siya at time 7. At time 7, titignan mo na dito kung sino-sino yung mga dumating ng 7 o mas mababa sa 7. So, meron tayo ditong P1 at P2. At kung i-check natin, mas mababa yung burst time ni P1. So, meron po siya ditong 4. So, pag add natin at magiging time 11. So, titignan ulit natin dito kung sino yung mga dumating at time 11. So, meron ulit tayo ditong si P2 at P3. Then, kung i-check natin is mas mababa yung burst time ni P3. At mag-e-end siya at time 15. So, at time 15, meron po ulit tayo ditong si P2 at si P5. So, mas mababa yung burst time ni P5. Meron siyang burst time na 6. So, mag-end time siya at 21. So, ang natitira na lang dito is yung P2. Then, ilalagay po natin dito sa may last. At mag-end time siya at 30. Determining length of the next CPU burst. So, it can only estimate the length. Can be done by using the length of previous CPU burst using exponential averaging. So, the small letter t here is the actual length and the aqua meaning the predicted value for the next CPU burst. So, this is the entire formula of the exponential averaging. So, this is the prediction of the length of the next CPU burst. So, from 6, mapupunta siyang 4. Then, from 4 to 6, then 6 to 4. Then, mapupunta siya sa 13. So, here is the example of the exponential averaging. So, A is equal to 0. Then, the recent history does not count. Then, A is equal to 1. Only the actual last CPU burst counts. So, if we expand the formula, we will get this. So, here is the formula and the solution. So, since both A and 1 less A are less than or equal to 1, each successive term has less weight than its predecessor. The priority scheduling. So, a priority number or the integer is associated with each process. The CPU is allocated to the process with the highest priority. The small integer is equal to the highest priority. So, it's either preemptive or non-preemptive. So, note that SJF is a priority scheduling where priority is the predicted next CPU burst time. So, the problem is the starvation. So, starvation is low priority processes may never execute. So, the solution will be the aging. So, aging as time processes increase the priority of the process. So, next is the round robin. So, each process gets a small unit of CPU time or the time quantum, usually 10 to 100 milliseconds. After this time has lapsed, the process is preemptive and added to the end of the ready queue. We can predict wait time if there are n processes in the ready queue and the time quantum is q. Then each process gets 1 divided by the n of the CPU time is in chunk of at most q time units at once. No process waits more than n less 1 q time units. The performance will be q large or the FIFO, then q small may hit the context switch wall. So the queue must be large with the respect of the content switch, otherwise overhead is too high. So ito yung example ng round robin. Then imagine na lang na pare-pareho yung mga arrival time nila. So unahin natin dito si P1. Si P1 ay may CPU burst na 17. Then, yung time quantum natin is 3 millisecond. So, 17 minus 3 is equal to 14. So, ilalagay natin dito sa may end time is 3. Then, P2, 3 yung CPU burst. So, 3 minus 3 is equal to 0. So, tanggal na si P2. So, ang end time niya is magiging 6. Next is si P3. So, 6 minus 3, yung quantum time, is equal to 3. So, si P3 ay mag-end time ng 9. Next is yung P4. So, P4 is magiging negative siya since 2 lang yung CPU burst and 3 yung time quantum. So, yung end time niya is magiging 9 plus 2 is si P4. So, 9 plus 2 is equal to 11. So, tanggal na din si P4. So, since round robin to, uulit or tataas siya sa may P1. Then, si P1 is may naiwan pang 14 na burst time. So, ililess natin siya into 3, yung time quantum natin. So, 11 yung magiging end time niya. 11 end time siya ng 14. So, next is yung P3. So, 3 less 3 is equal to 0. So, end time niya is 17. Then, balik sa P1. So, yung 17 na end time plus yung 11 na natitira sa may P1 is yun na yung magiging end time natin. So, 17 plus 11 is equal to 28.
Time quantum and context switch time. So in this figure, we can see on how a smaller time quantum increases context switches. The performance of the RR algorithm depends heavily on the size of the time quantum. At one extreme, if the time quantum is extremely large, the RR policy is the same as the FCFS policy. In contrast, if the time quantum is extremely small, say 1 millisecond, the RR approach can result in a large number of context switches. Assume, for example, that we have only one process, 10 time units. If the quantum is 12 time units, the process finishes in less than 1 time quantum with no overhead. If the quantum is 6 time units, however, the process requires 2 quanta, resulting in a context switch. So, if the time quantum is 1 time unit, then 9 context switches will occur, slowing the execution of the process. So next, turnaround time varies with the time quantum. So turnaround time also depends on the size of the time quantum. As you can see in this figure, the average turnaround time of a set of processes does not necessarily improve as the time quantum size increases. In general, the average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. For example, giving 3 processes of time 10 time units each and quantum of 1 time unit, the average turnaround time is 29. So, if the time quantum is 10, however, the average turnaround time drops to 20. And if context switch time is added in, the average turnaround time increases even more for a smaller time quantum since more context switches are required. So, next, multi-level queue. Ready queue is partitioned into separate queues, which is the foreground or interactive and background or batch processes. So these two types of processes have different response type requirements, and so many have different scheduling needs. In addition, foreground processes may have priority, which is the externally defined over background processes. So each queue has its own scheduling algorithm. So the foreground queue might be scheduled by an RR algorithm while the background queue is scheduled by an FCFS algorithm. So scheduling must be done between the queues. Fixed priority scheduling serve all from foreground, then from background. Possibility of starvation. So time slice. Each queue gets a certain amount of CPU time with which it can schedule amongst its processes. So 80% to foreground in RR and 20% to background in FCFS. Next, multi-level queue scheduling. So as we can see in this figure, an example of multi-level queue scheduling algorithm with 5 queues. So listed below in order of priority. So first is system processes, second interactive processes, third interactive editing processes, fourth batch processes, and student processes. So each queue has absolute priority over lower priority queues. No process in the batch queue, for example, could run unless the queues for system processes, interactive processes, and interactive editing processes were all empty. If an interactive editing process entered the ready queue while a batch process was running, the batch process would be preempted. So next, multi-level feedback queue. A process can move between the various queues. Aging can be implemented this way. So, multi-level feedback queue scheduler defined by the following parameters. So first is number of queues, scheduling algorithms for each queue, method used to determine when to upgrade the process, method used to determine when to demote a process, method used to determine which queue a process will enter when that process needs service. So, the definition of a multi-level feedback queue scheduler makes it the most general CPU scheduling algorithm. So, it can be configured to match a specific system under design. And unfortunately, it is also the most complex algorithm since defining the best scheduler requires some means by which to select values for all the parameters. Next is example of multi-level feedback queue. So we have here three queues, which is Q0, Q1, and Q2. So Q0, which is RR with time quantum 8 milliseconds, Q1 RR time quantum 16 milliseconds, and Q2 FCFS. So next, scheduling. A new job enters Q0, which is served FCFS. When it gains CPU, job receives 8 milliseconds. If it does not finish in 8 milliseconds, job is moved to Q1. So at Q1, job is again serve FCFS and receive 16 additional milliseconds. If it is still does not complete, it is preempted and moved to Q2. So multi-level feedback queues. So this is the example. A process entering the ready queue is put in Q0. A process in Q0 is given a time quantum of 8 milliseconds. If it does not finish within this time, it is moved to the tail of Q1. If Q0 is empty, the process of the head of Q1 is given a quantum of 16 milliseconds. If it does not complete, it is preempted and put into Q2. Processes in Q2 are run on a FCFS basis but are run only when queues 0 and 1 are empty. So, this scheduling algorithm gives highest priority to any process with a CPU burst of 8 milliseconds or less. Such a process will quickly get the CPU, finish its CPU burst, and go off to its next I/O burst. Processes that need more than 8 but less than 24 milliseconds are also served quickly, although with lower priority than shorter processes. Long processes automatically sync to Q2 and are served in FCFS order with any CPU cycles left over from queues 0 and 1. Next, thread scheduling. Distinction between user level and kernel level threads. So, user level threads are managed by a thread library, and the kernel is unaware of them. So, to run on a CPU, user-level threads must ultimately be mapped to a associated kernel-level thread, although this mapping may be indirect and may use a lightweight process. So, next, many-to-one and many-to-many models thread. Library schedulers user-level threads to run on LWP, known as Process Contention Scope or PCS, since scheduling competition is within the process. So, when we say that thread library schedulers user threads onto available LWPs, we do not mean that the threads are actually running on a CPU. That would require the operating system to schedule the kernel thread onto a physical CPU. Next is kernel thread scheduled onto available CPU is System Contention Scope or SCS, competition among all threads in system. So, competition for the CPU with SCS scheduling takes place among all threads in the system using the one-to-one model such as Windows, Linux, and Solaris scheduled threads using only SCS.
So next is the pthread scheduling. So API allows specifying either PCS or SCS during thread creation. So pthread scope process schedules threads using pieces scheduling, and pthread scope system schedules thread using SCS scheduling. So you can use the pthread scheduling features to set up policies that determines which threads the system first select to run when the CPU cycles become available, and how long each thread can run once it is given the CPU. Scheduling is necessary in real-time application in which some threads have more important work than others. For example, a thread that controls equipment of a factory floor could be given priority over the threads doing background processing. The pthread standard defines scheduling is as an optional feature. So this is an example of syntax of pthread scheduling using API. So the program below demonstrate the use of pthread as well as the use of number of other scheduling related pthread function. So in the following run, the main thread sets its scheduling policy with a priority of 5 and initializes a thread attributes object with a scheduling policy attribute. Then the program set with a specific attributes, and if the threads are created using this attributes object, then that it should take their scheduling attributes for the thread object, and the program then creates a thread using the thread attributes object, and that thread displays its scheduling policy and priority. So multiprocessor scheduling. So CPU scheduling is more complex when multiple CPUs are available and homogeneous processors within a multiprocessor. Asymmetric multiprocessing is only one processor accesses the system data structure, alleviating the need for data sharing. And symmetric multiprocessing or SMP, each processor is self-scheduling all processes in common ready queue, or each has its own private queue of ready processes. And processor affinity, process has affinity for processor on which it is currently running. So there is two types of processor affinity, which is the soft affinity and the hard affinity. So in multiprocessing scheduling, it focuses on designing the system scheduling function, which consists of more than one processor. So multiple CPU share the load in multiprocessor scheduling, so that various processes run simultaneously. In general, multiprocessor scheduling is complex as compared to single processor scheduling. In the multiprocessor scheduling, there are many processors and they are identical, and we can run any process at any time. So this is the diagram of NUMA and CPU scheduling. So NUMA is what we call the non-uniform memory access, is a computer memory design used in multiprocessing where the memory access time depends on memory location relative to the processor. So the main memory architecture can also affect processes affinity. If particular CPUs have faster access to memory on the same chip or board than to other memory loaded elsewhere. So that the non-uniform memory access NUMA as shown below, if a process has an affinity of for a particular CPU, then it should be preferentially be assigned memory storage in local fast access areas. So the multi-core processors. So recent trend to place multiple processor cores on same physical chip. And multiprocessors are faster and consume less power, and multiple threads per core also growing. It takes advantage of memory stall to make the progress on another thread while memory retrieve happens. So this is the diagram of a multi-threaded multi-threaded multi-core system. So, the recent trends are to put on the CPU, which appear to the system as multiple processors, and the compute cycles can be blocked by the time needed to access memory whenever the needed data is not already present in the cache, as shown in the figure below. As much as the half of the CPU cycles are lost to memory stall. So next is the operating system example. So first, what is operating system? So operating system is a software that supports a computer basic functions such as scheduling tasks, executing applications, and controlling peripherals. So the first example here is the Solaris scheduling. So Solaris scheduling is a scheduler that provides a real-time scheduling policy. And real-time scheduling enables users to assign fixed priorities to specific processes. And the highest priority real-time user process always get the CPU as soon as the process is runnable. And next is the Windows XP scheduling. So Windows XP uses a priority-based preemptive scheduling algorithm. The dispatcher uses a 32-level priority scheme to determine the order of the thread execution that is divided into two classes, variable class from 1 to 15 and real-time class from 16 to 31. And last is the Linux scheduling. So the Linux scheduler is a multi-queue scheduler, which means that for each of the logical host CPUs, there is a run queue of processes waiting for the CPU. Each virtual CPU waits for its execution in one of these run queues. Moving a virtual CPU from one run queue to another is called a CPU migration.
Good day, sir. I'm Avel and Malvar from 4ABA. To be continue, Windows XP priorities. If you can see in this table, there are a real-time class, high, above normal, normal, below normal, and idle priority. And time critical, highest, above normal, normal, below normal, lowest normal, and idle. Let's tackle Windows scheduling threads. Using a priority-based preemptive scheduling algorithm, the Windows scheduler ensure that the highest priority threads will always run. The portion of the Windows kernel that handle scheduling is called a dispatcher. A thread is selected to run by the dispatcher will run until it's preempted by a higher priority threads until it terminates, until its time quantum ends, or until it calls a blocking system call, such as for I/O. If a higher priority real-time threads become ready while a lower priority threads is running, the lower priority threads will the preempted. This preemption gives a real-time threads preference access to the CPU when the threads need such as access. The dispatcher uses as 32 level priority chain to determine the order the threads execution priorities are divided into two classes. The variable class contains threads having priority from 1 to 15, and the real-time class contain there are with the priorities ranging from 16 to 31. There is also threads running at the priority 0 that is used for memory management. The dispatcher uses a queuing for each scheduling priority and traverses the set for queues from highest to lowest until it find threads that is ready to run. If no the ready threads is found, Now, the dispatcher will execute special threads called the idle threads. There is a relationship between the numeric priorities of the Windows kernel and the Windows API. The Windows API identifies the following 6 priorities class to which a process can belong. This is the 6 idle priority class, below normal priority class, normal priority class, above normal priority class, high priority class, and the real-time priority class. The processes are typical members of the normal priority class. A process below to this class unless the parent of the process was a member of a idle priority class, or unless other class was specified when the process was created. Additionally, the priority class of a process can be altered with the set priority class. Threads within the given priority class also has a related priority. The value of the relative priority includes the idle, lowest, below normal, normal, above normal, highest, and the time critical. Next. The value of the priority classes appears in the top row. The left column contains a value of the relative priorities. For example, this one. If the relative priorities of threads is the above normal priority, class is normal. The numeric priority of the threads is 10. Further, each thread has a base priority representing the value of a priority range for the class. Priority is the value of the normal relative priority for the class. The class priorities for each priority class are this following. Ito po yan. If you can see, the real-time priority class and the normal is 24. And highest priority class is 13. Above normal priority class, 10. Normal priority class, 8. Below normal priority class, 6. And the idle priority class is 4. Next, you can see in the table, there are the priority, time quantum expired, and the return from sleep. So, what is the priority? The class-depending priority for the time-sharing and interactive class. A higher number indicates a higher priority. Next, the time quantum. The time quantum for the associate priority, this illustrates the inverse relationship between priorities and the time quantum. The lowest priority is 0. As the highest time quantum, the 200, if you can see, 200 milliseconds, and the highest priority is the 59. As the lowest time quantum, you can see the 20. Next is the time quantum expired. So what is the time quantum expired? The new priority of a thread that has used its entire time quantum without blocking. Such threads are considered CPU intense. As shown in the table, these threads have their priorities lower. And the returns from sleep, the priority of threads that is returning from sleep, such as from waiting for 1 to 0. As the table is stated, when I/O is visible for waiting threads, its priority is boosted to between 50 to 59, supporting the scheduling policy of providing good response time from interactive process. Next, Solaris scheduling. If you can see that in the table, global priority, the highest and the lowest. The highest is 169 and the lowest is 0. In scheduling order, first and last. The fixed priority and fair share classes were introduced with the Solaris. Threads in the fixed priority class have the same priority range as those in the time sharing class. However, the priorities are not dynamically adjusted. The fair share scheduling class used a CPU shared. Instead of priorities to make a scheduling decision, CPU shared indicate entitlement to available CPU resources and are allocated to a set of processes. Each scheduling class includes a set of priorities. However, the scheduler convert the class-specific priorities into global priorities and selected the threads with the highest global priority to run. The selected threads runs on the CPU until it's one block. The user is time slice or it's preempted by higher priority threads. If there are multiple threads with the same priority, the scheduler used a random round robin. Next, Linux scheduling contains order 0 to 1 scheduling time, 2 priorities range, time sharing, and real time. Next is real time range from 0 to 99 and nice value from 100 to 140. Next is priorities and time slice length. Numeric priority is 0 to 99 and the highest relative priority and the highest is 0 to 99 and the lowest is 100 to 140. Real-time tasks and order tasks. Time quantum 200 milliseconds and the lowest is 10 milliseconds. Next, algorithm value evaluation. Deterministic modeling takes a particular predetermined workload and defines the performance of each algorithm for that workload. Queuing models and implementation. What is the queuing models? A queuing theory is the mathematical study of waiting lines or queues. A queuing model is constructed so that queuing length and waiting time can be predicted. Also, what is implementation? Implementation is the execution or practice of a plan, a method or a design, idea, models, specification, strand, or a policy for doing something, such as implementation in the action that must follow any preliminary thinking for something to actually happen. List of tasks indexed according to priorities. Active arrays, priorities 0 to 1. Task list, expired arrays, priority 0 to 1. Task list is 140. Next, you can see in the table the actual process execution. The CPU is the 10. The I/O is 213. The CPU again is the CPU is go to simulation, FCFS, performance statistic, and the CPU 10 and I/O 112 simulation SJF, the performance decision for SJF. A distribution driven simulation may be inaccurate. However, because of relationship between successive events in the real system, the frequency distribution indicates only how many instances for each event occur. It does not indicate any time about the other of their occurrences.